Hello people, Zach here again today, and this is going to be the first physics video that I've done in a long time. I have to excuse the poor lighting. I'm kind of recording from my phone right now, but let's go ahead and get into the meat and potatoes of this. So I had this video show up in my feed. It's about this question, and I've seen this question before. I was talking about what would happen to the Earth if the sun just like magically disappeared instantaneously. And the person who was making the video was talking about like, oh, hey, if the sun disappears, like it actually like 7 minutes before the Earth actually starts moving off of the trajectory because gravity can't move faster than the speed of light or some crap like that. Well, one, like that wouldn't even be true to begin with because like consider like space-time expansion. So if space-time is expansion is the thing and we can observe galaxies moving away from us faster than the speed of light, and gravity is supposed to be based off of like space-time curvature, that makes no sense why it would be limited by the speed of light. That's like an inconsistency in the theory itself. But let's just negate that for a minute. Gravity is not a particle, and gravity is not a wave. Gravity is an acceleration. It's the acceleration of one thing towards another. If there is nothing to accelerate, there is no acceleration. And when it comes to angular motion is always an acceleration. And we know from Newton's first law that an object in motion stays in motion unless acted upon by an external force and continues in a straight line at a constant speed. So if you eliminate the sun, the Earth should continue in the direction of its current momentum in a straight line at a constant speed. It's not going to continue orbiting nothing, because that would be an acceleration and it would violate Newton's first law. Now, I'm sure that people are already ranting in the comments, saying that, well, what about space-time curvature, because like the gravitational wave has to propagate out there or something like that. Now, this is where we're going to get into the topic of space-time curvature. It's imaginary. It's like equipotential lines in an electric field, or like magnetic flux lines, or like contours in a topological map. And now I'm going to go ahead and explain this and see where you can see where it's actually coming from. So imagine that like my job is like it's like 15 miles away, I think. And it takes me 20 minutes a day to get there. And I try to 3 different speed zones to get there. One speed zone is 25 miles per hour. One speed zone is 45 miles per hour. And one speed zone is 55 miles per hour. Now, the average speed for the whole trip is 45 miles per hour. So if you work out the math, 45 miles per hour times 20 minutes, it's 15 miles away. Works out fine. Now, the speed of light is actually the rate of induction of an electromagnetic field. Okay? And this is why it's directly proportional to the dielectric permittivity of free space, and the dielectric permittivity and the magnetic permeability. That's basically like the ability to establish dielectric and magnetic fields in space. Now, when light transitions from one medium to another, where the permittivity and permeability of that material changes, its speed changes. And this causes a refraction in the light. So like if you're passing from air into water, or from glass into something else, like air, that's change in the speed of light causes the light to refract and bend in a certain direction. So we know that light changes like that. Now, also apparently, we've observed gravitational lensing, and what that is the refraction of light caused by gravity. Now, ignore whatever explanation you think that there is, because the observation, what we're observing, is that the light is refracting. And refracting is a change in direction, which is an acceleration, which means that when the light enters this gravitational potential field, whatever you want to call it, it's refracting. It's changing direction or changing speed. Now, we cannot know the exact refractive index at every single location in the entirety of space. It's just not possible. But let's say we make the assumption that the speed of light is always the speed of light in a vacuum, even though we know for a fact that can't be the case, because this light is passing through like nebulas, or passing through gases or plasmas, or just being refracted by the gravitational field itself. So we know that it can't actually be the same, but we can assert it's the same. Okay, what is the effect of this going to be? Well, let's go back to the car example. The optimum speed of light, which is the speed of light in a vacuum, I can't remember the exact number off the top of my head, but the optimum speed of our car would be 55 miles per hour. That's the fastest it's ever going to go. That's analogous to the vacuum speed of light. That's nothing in the way, the maximum speed all the time. If we tried to do our calculations saying, well, it takes us 20 minutes to get there, and I'm going 55 miles per hour, how far away is it? It's 18.3 miles away. That's not 15 miles. I know it's 15 miles, but according to my calculations, it's 18.3 miles. Where did that extra 3.3 miles come from? Well, we've defined that our car is going 55 miles per hour, which means it can't be speeding up or slowing down. So there is only one logical explanation, right? It's that where the road, it has steep hills that I'm constantly driving up and down, going down, up and down these roads, right? Because that adds a vertical component to my travel, which increases my distance by 3.3 miles, right? Math all works out. It's just, all it is that I'm going down steep roads, right? Wrong. We know that's not the case. And the real explanation is that the speed I'm driving at is changing. Sometimes I'm going 25 miles per hour, sometimes it's 45, sometimes it's 55. Average speed is 45. But it's because we considered only the optimum speed, which was the 55 miles per hour, that it's created this 3.3 mile difference. And the only other way we can explain it, if we are asserting that we are moving 55 miles an hour, is that we have to consider the topology of the road. And it's the same thing with spacetime curvature. We are asserting that the light is moving at a constant speed, which is its most optimum speed, when in reality, space is not a perfect vacuum. There's like 0.000 or something like 3 pascals, which is like random debris, and it's moving through like atmosphere and space dust and all the different kinds of crap that's out there that's affecting its speed, or even just the gravity of gravitational potentials of these large bodies that are affecting its speed. So it's not moving at a constant speed. We know it's not because we see the refractions, but we're asserting it is. And so the only way that we can explain the observation is by asserting that there is a topology to the spacetime, but that topology is not real. For the sake of our calculations, it helps. If we can imagine that it's real, then yeah, we can kind of sort of trace out how the light would behave, because if it went through that way one time, it's going to go through the same way the second time. But it doesn't mean that the curvature is real. It's imaginary. That's all. Thank you for watching.